Okay, good afternoon. So, what I'm going to tell you about this afternoon should only take something like 45 minutes. So, you can either we finish early, or Jean-Francois is willing to fill in some of the details of his quantitative model that he didn't get to this morning, if people would like to hear that. Okay, so. I want to tell you about a very simple system which gives it's a way of getting interesting three-dimensional shapes from patterned two-dimensional systems. So this is a paper, you can find it on the archive here. It's with two students. Duan Duan Wan is here, so you can ask her all about technical details of this work. Tao Zhang is another student at Syracuse, and with my colleague Jen Schwartz. Okay. This is going to be about basically fluids, simple patterns of fluids that can change their shape. Here is shown some kind of fluid system. Anyone have an idea what that is? Yeah, it looks like cells. It does look like cells. And one of the inspirations for this work will be trying to mimic some of the interesting cooperative behavior you find in cells in tissue. Okay, cells are the components, tissue is the collective objects. Okay, but it's not actually cells. Any other guesses? Foam is close. It's close. It's something similar to a foam. Emulsion. It's some kind of emulsion. You guys did a lot of cooking here. I know you had. What was that? Mayonnaise. That's mayonnaise. Very good. That is mayonnaise. Electron micrograph of mayonnaise. So what is the? What's the scale? It's well. These are millimeters. It's not on here, but this is real. I mean, it's electron micrograph of real mayonnaise. So. A millimeter. Yeah. Droplets are huge in mayonnaise. But not millimeter. You can see millimeter with your eye. Yeah, you can almost in mayonnaise. Really? Yeah. The smallest are probably microns. Well, I mean, what's this fluid in here for mayonnaise? Oil, right? It's oil, and the other. So this is oil in something emulsion. Well, and what's the other fluid? What? No, it's not egg white. Yes, more or less water or vinegar is usually used. Okay? It's a good exercise if you want to understand emulsions to make mayonnaise by hand, because you start with the vinegar. I did it as an exercise in soft matter, and you have to beat up the olive oil a lot, right, to make these very small droplets. I suppose they can get down to tens of microns, probably, is what I mean. So I just grabbed this one off the web. But you can find electron micrographs in the book of Harold and McGee, Food and Cooking, which are very nice. So this is an oil and water or vinegar emulsion. That must be this one, yeah. Yeah. Doesn't matter. He has electron micrographs with very small droplets. But there is an interesting ingredient which you also mentioned, which was a lecithin, right, or egg yolk. So to stabilize emulsions, you like to put in something which lowers the interfacial energy between two sort of incompatible fluids, oil and water in this case. And for mayonnaise, that's played by a molecule, a lipid, lecithin, that's found in egg yolk. So that's why you have some egg yolk in there. I'm actually going to be talking about the opposite kind of emulsion. So it's going to be water droplets in oil. Here's a picture of a nice water droplet. So this work was inspired by a really nice science paper from the group of Hagen Bailey in Oxford. So this is what they do. Okay. They use a droplet printer shown here, and they inject water droplets into oil, and they're picoliter volume droplets, so very small, and you can print thousands or tens of thousands of these droplets into the oil in some pattern, usually in some planar pattern. So there's here's droplet going in, it's on a micromanipulator stage, and you can move that stage back and forward. So the nozzle is sort of fixed, and you're moving this back and forward, so you can generate layers, planar layers of these droplets. Now the oil has lipids in it, okay, so that's playing the role of the surfactant. So what happens is you have a water droplet like this, and a single water droplet, since you're printing it into the oil with lipids, is going to pick up a monolayer of lipids. Okay, so lipids look like this, with one or two or even three tails, and they have a polar head like this, and they have a fatty acid chain, which is apolar. So this polar head likes to live in water, and the chains like to stick outside like this. So that will be a single water droplet. So now if you bring two of these close enough together, you can form here a bilayer, like the bilayer you find in cells. So this bilayer gives you an attractive interaction between droplets, which makes a junction, quite a stable junction between droplets. So here is shown now an array of droplets. Just focus on these blue ones for the moment. An array of droplets which make a cohesive network with the junctions, now these lipid bilayers now. Yeah?
What about the tails that tracks?
The tails that what?
What about the tails tracks? Do the particles attract each other through the bilayer?
Yes. So let me draw it again. I didn't draw it very well. So if you have one like this, and then you have another water droplet here with these things sticking outside, then because of electrostatic interactions and entropically, it's favorable for these two hydrophobic fatty acid chains to come close together and merge into one. Was that the question? So that's the junction. Yeah, that's fine. But with a surfactant. But this is, yeah. I mean, it functions as a surfactant when they combine. But since you imprint it into oil that's saturated with these lipids, the water droplets come naturally with this monolayer. And then there's a natural adhesive interaction that bonds the droplets together to make a network. That's the only point.
No, but sometimes you can have inverse emulsion where the droplets don't.
Yes, well, here they attract.
And that just has to do with the chemistry.
Simple electrostatics of the lipid monolayer, because those you can lower the free energy by making the droplets come closer together and putting because that excludes water. It's a kind of sort of like a depletion interaction. Yes?
So is the hexagonal shape, is that for the last process, or you can actually
You mean of the actual droplets? You mean of the actual droplets, or the long-range translational order of the things? Yeah. So what happens is that two round droplets that come together will have an interface with some contact angle like that. That's sort of flatter. So that's all that's being shown there. And the mean separation between droplets is going to be, favored separation is going to be less than the sum of the radii of the droplets because of this interaction. So the interface flattens out a bit. That won't be important for us that much, but except for modeling it. Now, that's not going to do much for you, except for making a nice network of these things. Well, actually it can. So this Bailey group, they're experts on pores. Someone was asking, I think it was, Jenny was asking if anyone works on pores, but they're experts in pores. So they're interested in, for example, you can put proteins into this lipid bilayer and make pores which form electrical junctions. So you can sort of electrify this network, okay, and have some kind of a functional network. But here we're going to be mostly interested in Yes, they do. They do that in this paper. They don't go very far, but they show that you can do it. So you can. It's not really active. Yeah. So we need one extra ingredient to introduce something interesting to these networks. And so for that, we're going to consider two species of droplets. That's what they also did here. So imagine that we have some iron that's dissolved, some salt that's dissolved in these droplets. So we'll consider two species, just two species of droplets, the one that has high concentration and one that has low concentration. Okay. By the way, you can estimate the Young's modulus of these kind of droplet networks, and it's 100 to 200 pascals. So it's a very soft system. Jean-Francois was discussing moduli for tissue and cells in his lectures. This has Young's modulus that's comparable to brain or fat or very soft tissue. So these things should be relatively easily deformable if you do something interesting to them. And that's the idea behind having these two concentrations of droplets, because then you're going to have osmosis. You're going to have water flow that goes from one droplet to another, from low concentration droplets to high concentration droplets, and that's going to cause them to swell. Okay? And that can drive shape change. So this is the whole idea behind what we study here. So how do you model a system? You can just model it as a sort of an elastic network. So there's some kind of spring constant K. You have a separation between droplets I and J. And as I said, because of this attractive interaction provided by the lipid monolayers making a bilayer, the equilibrium separation is a little bit less than the sum of the radii. So we take it to be about 80%. So there's a factor in here of 80%. If they come close enough within a separation that's less than the sum of the radii, this kicks in. Otherwise, its energy is zero. And then the only other ingredient is going to be water flow, described by Fick's law, when you have these two droplets of different concentration being connected in this spring network here. So there's going to be a flow of current, volume per unit time, that's controlled by the interfacial area that's shared by two neighboring droplets. And then it's going to be driven by the osmolarity gradient. And then you can just model with some kind of damped dynamics the motion of a particle as it swells, and this forces act on it due to this energy. So that's just modeled by the derivative of this energy, a damping term, and then you can study this, for example, with molecular dynamics. This is an overdamped system. It's sort of, it's just, yes, and yeah, this is force on droplet I. So it moves and dissipates. These systems are pretty much in Stokes regime. So it's yeah. So this is acting on I. Yeah. Okay. It's relative velocity. So so let's see what happens here. So let's look at a very simple case. I call it sort of the bimetallic strip analog of this system. So we have one planar layer of high concentration droplets shown in red on the bottom, and on top of it is another planar layer or strip of these low concentration droplets. So here the red ones have a concentration of 1 in some units, and the top one has a concentration of 0.5 in some units. So this concentration gradient is about 0.5. So what do you think is going to happen in this case? Yeah.
Water will flow into one layer and fatten it.
Right. So it's going to flow from the top to bottom, right? So the bottom ones are going to swell. So yeah. So you had something sort of. Did you mean like with it'll curve, right? But should be sort of even, right? I mean. So let's take a look at that. The colors here also show that the osmolarity is changing, so that this one is lowering, it's becoming whiter, and it's starting to equilibrate with this one. So on the outside, these droplets are swelling. On the inside, they're shrinking. So if you compare these two layers here, you want the fatter ones to be on the outside because the radius of curvature on the outside is bigger than the radius of curvature on the inside. So this deforms into this nice spherical shape. And you can compute the radius of curvature of this deformed strip. It's proportional to 1 over this concentration gradient. And you can see here the concentrations are starting to equilibrate. Now, you can do that also, so you can try this. Take a strip of, let's see how well this works. If you guys have paper, take a small strip of paper from your pads and try to flatten out your hand and put it on your hand. Okay. You need a little bit of patience for this. What? You need a steady hand. Try it. Come on, you guys. You don't have any paper? He has paper. No Twizzlers. Okay.
Oh, look at this.
That's too big. That's too big. Smaller piece of paper.
Smaller.
That should be good. Hold out your hand. Boulder's what?
Oh, very small.
I made it fairly small, but you can try that. Try that. We can try. Well, let's see if anything happens first of all. Is anyone getting anything? Wait.
Yeah.
Anybody?
Matt, what are we supposed to see in this?
Okay, Matt.
You know, after
That's
this
cheating.
was Vladimir, this is a bit underwhelming.
Wait. Yeah, you got to have patience. Experiments in it.
Is this why the talk's 45 minutes? So
Yeah, that's right.
45 for this time.
You need plenty of time. Was that working?
Is it just sticking to my hand and nothing else is happening?
No, it's not. Yeah, so
I think it's working.
is yours working?
Kind of.
Yeah, his is going up. Yeah. Starting to curve. Wait a little bit more. Mine's curving a bit. Okay.
Oh, is it meant to cut in?
No, it should curve outwards. So paper is hygroscopic. It absorbs moisture, and your hand sweats a little bit. So the paper will absorb water from your hand and swell with the same mechanism. He has it.
It's working.
Yeah,
I think it's working.
it's working. And just wait a little bit. Once it gets going, we can. Anyone else? Yeah. So if you okay, so Christina was suggesting this to theorists cheating. You can breathe on your hand. It's best if you're like nervous, you know. You start sweating a lot. Just should pretend that you're going to walk on coals or something. Mine's curving up quite a bit.
But eventually it will come flat.
Aha! That's a good. So this is a good point. So we'll come back to that. You mean because of evaporation?
Well, or because the gradient is going to become small.
No. No, it absorbs on the outside. It doesn't absorb all the way through.
Well, then wouldn't it eventually go evenly?
Or through the paper? Yeah, if it diffuses all the way through the paper, then it will flatten again. But there's another effect also that can happen here, and I'll come back to that. So you can test this also with, I mean, I made this sponge wet. So yeah, so that happens there. The sponge is too wet, it goes all the way through. But what?
The sponge itself.
The sponge itself is doing it, yeah. That's also true. The whole sponge is an example. Yeah. We can try some paper on this. Now this is actually studied by the group of Mahadevan at Harvard. It's yours. And you can get this paper to flop up, to bend up so much it flops over onto itself. It can actually move along the surface this way. So they're studying this as an example of some kind of generated motion from this kind of simple effects. It bends, can bend up so much like this that it flips over.
Okay, but then that's it. Or it continues to look like.
It can continue, and so there'll be so we'll come back to this issue of reversibility, because what I'm going to show you at the moment, it looks very one way, non-reversible. So you can now just start playing with the kinds of various geometries. The experimentalists even did this one, so that you can put these into this kind of pedal shape. It folds up, and you can use it for an. That was a simulation, but the experimentalists actually did this. So on the left is the experimental panel here, and that's the folded up thing.
You put the water on. You put the drop of water on top.
Here is exactly the system I described. So here the orange is the red. It's a bilayer, two planar layers. Blue is the low concentration, orange is the high concentration one. printed, 1,000 droplets here, 1,000 droplets above, with just different osmolarity. Those are real experimental images.
What's the scale for?
Yeah, so. Okay, so these are micron-sized droplets, picoliter volume.
So the whole thing is like that.
So these are millimeter. Yeah, it's a millimeter.
So is it happening due to the evaporation?
No, exactly the same mechanism I described here. Water flow to the high concentration droplets, which causes them to swell. Here, this is all they're doing. See, the outer ones are swelling. They like to live on the outside with larger radius of curvature. It's just being done on 4 petals. Four pieces of what I showed you before. 4 of these bimetallic strips.
So this is printed droplets.
Yes.
They have a different ionic strength.
Yes, they print 2 species of droplets. That's all you need. High and low concentration droplets. So they have potassium chloride, different concentrations inside the droplet. So if you go back, there are actually 2 nozzles here. So you use these two printing nozzles. Print each. And you print them down here. So they program the geometry by how you move this stage to get the initial setup. So for this case, you print out these 4 arms. Question? Yeah.
In this one, it looks like, how many layers does it start out?
Okay, so this one has a dub.
Seems like
This one has, yeah. So no, this has a 2 layers on top, 2 on the bottom.
you can see some spheres as it folds passing into.
So they're just changing color. So you can see 2 all the way. The ones that are going white are equilibrating. So the concentration's starting to match.
If you watch the
There's a little-
the blue face, then you can kind of see some defects.
Some buckling, right? Yeah.
Yeah.
Yes. That happens, and we'll see that more. But we can do it again so you can see it and see what you mean. You're looking here.
More like the further 2. You can see right on the middle in the middle of the space.
Uh-huh.
I
Yeah,
see
they
some
won't.
of the spheres are being set
They can indent,
low,
yes.
trying to they're sort of buckling on a wavelength.
Yes,
It's the
yes.
scale of the
Yes, we'll see a nice example of that in a minute. So here's an example where we just take 2 lines now. Okay, so one-dimensional version of this. The concentration gradient is a bit higher here, and we do the same thing. Here you can get it to close up, that's one thing, and then you get this buckling, which is related to, I think, what you observed in the other system. So you can make a sort of a phase diagram of this system. So you can plot the 2 concentrations here. So this one is, in this case, we fixed C2, the red one, the high concentration one to be 1, and varied C1. And so the possibilities are the rings don't close. You can get a closed ring that doesn't undergo that last stage of buckling, and you can get a closed ring which buckles. So you see here, this is just, so the as we go down here, we get a higher concentration gradient. So that favors unclosing. So we go here, you move around in this phase diagram. These are the 3 possibilities you can get. And you can basically, just with Euclidean geometry, work out when these kind of situations are favored. So it's a function. Along here, we're varying also the number of droplets in the row. Okay, so going down this way, we're varying the osmolarity gradient. Going this way, we're varying the number of droplets So as you go out this way, increasing droplets, you have a bigger region of this closed but unbuckled ring, and it requires a critical osmolarity gradient. So you can just write down when spheres you only have 2 radii to work with, and then the number of droplets will determine the circumference, and you can see when you can write down just Euclidean geometry conditions for getting these kinds of states, and the threshold or the crossover between these two is shown with these triangles here and these squares here, and you can see it fits very well the simulation. So it's basically just geometry. The mechanical relaxation that makes the network happens pretty rapidly here. It's controlled by just this adhesive interaction, and then the flow occurs much more slowly and experimentally in times of minutes or hours. So this is just kind of the setup you have to do to get a closed geometry of these 2 radii, and you can work out those conditions. Yeah.
So is this simulation only based on 2 dimensions?
No. I mean, the initial setup is 2-dimensional, but then you track the centers of each droplet, and then you just assume it's basically a sphere with that volume. Yes. So you can do that. So the whole idea here is to try to generate interesting 3D geometries like that. So in fact, that's what we'll do here. So what else can you do? So I showed you before just basically a unidirectional osmolarity gradient, but here where we can look at gradients in more than one direction. So here's a case now where it's bending in, gradient across this way. Finally closes. So that's putting the gradient in this way, so it's bending around like that, with the flow radially outward. So it's what I call slab closure. Yeah. Molecular dynamics. Yeah. We're not looking at ground state configurations, just evolving according to that force law. So here's a little bit more complicated system. We now so that was again, this one was just flow from flow out this way. So it was again basically unidirectional, but bending in different direction. So here in the next one, we have a concentration gradient that goes across this N in this N direction and in this L direction. So that gives us 2 parameters to play with controlling this gradient. So now it can bend in 2 different directions, and that's going to try to get something of what you were asking for. So let's see what happens in this case. So now it's bending and twisting. So this generates this spiral-like configuration. Well, yeah, you mean the whole coiled?
Yeah, so like, does it have a stiffness?
Yeah. Yeah, you can try to estimate those. So the collective stiffness, right? Yeah, yeah. So this would be hard to print directly. That's the idea, right? But all you have to do is to print this guy and then let it evolve. That's the idea.
Again, how would one create these gradients?
So you need more than the two species then. So you have to have several different. So you have to put down droplets of one concentration in one direction. Yeah. So this is a little bit more sophisticated. So in the computer, it's easy. So that's what we're showing here. Just want to explore what shapes you can get. But yeah, in principle, you can do it the same way, right? You just have to lay down in layers all of these, and then the next layer different. So you have to look along the lines of constant concentration and print those droplets, and then print a droplet with a slightly different concentration along another line, and so on, by moving the stage. Yeah.
Question about the experiments. How do you lay down a layer of a different concentration on top of another one and finish printing before it starts?
Okay. So you can print pretty rapidly, and the mechanical networks, as I said, they form pretty quickly, and the flow is fairly slow, minutes or hours. So they're picoliter things, so you can print tens of thousands quite quickly. Yeah. And this experimental group wrote even dedicated software that control and their own printers to do this. So they're not commercial printers.
You have to polymerize them at the end to stabilize them.
Okay, so they're actually pretty stable. So these bilayer junctions are quite strong. But you could imagine doing more to the network. But they actually don't need to. They last for quite long times. So there's a lot of collective cohesion also in this. So this is the sense in which it's modeling tissue from cells. But you can do a lot more, as I said, to functionalize these networks once you have them. So let's do that one again. Let's go to the next one. So we mapped out basically, for example, the pitch and the radius of curvature of these droplets as a function of these gradients, parameters controlling the concentration gradient. So this was the one I called Kn, controlling the gradient along the n direction, and different figures here give different values of Kl. So you can vary the radius and the pitch of the spring or the spiral structure that you get. So you can of course vary the basic shapes of the arms that you're varying. So here we just use hinges. We have 3 hinges here and flat faces. Here you need a fairly strong hinge, so there's several layers in this hinge in order to give it the strength to fold up these layers. So this is like 4 layers going across here on the outside. So you can make shapes, like faceted shapes here, just from determined by basically the initial geometry of the setup. Okay, so now let's come back to this paper example, right? So these are all sort of irreversible processes, but in the paper example that we had, let's get another color here. You start with, where's the red? Here we go. Start with a flat piece of paper or a monolayer of droplets sitting on top of another one. Think of this one as a bottom one as a substrate in this case, and then imagine that you have this one here absorbing water. So this one is the high concentration one. Water is flowing like this. This one wants to swell and change its shape. So a minute later, a little bit later, you're going to have a shape like that, right? Let's draw it a little bit bigger. So after some time, you're going to have a shape like that. Now, something else can happen here, right? What else can happen to the water that's in the paper as it folds up? Yeah, it can evaporate to the environment. So you can also have fluid flow this way. So as it evaporates to the environment, it's going to shrink again, and it's going to want to reverse. Not only that, but this interface here is dynamically evolving. As it bends, more and more of the surface is exposed to the bulk environment. So you get greater rate of concentration. So that can eventually overcome the swelling, and it can start to shrink again and go down. So this gives you a way of making this process reversible. So that's what we exploit here. We also consider the solvent, so the environment out here. We take that of even higher concentration. So as the system bends, it starts to have fluid flow to the solvent and can reverse. So what's shown here is this in a slightly backwards order. So it's first folded, okay, and it's going to lose water to the solvent below this plane, and so it's going to unfold and fold up again. But the principle is exactly this one here. So this is a one-step reversible process. So far we haven't figured out how to cycle this, but at least it can be reversible. So this is the step also which Maha's group exploits with paper. Okay? So the paper can on a substrate fold up like that and then evaporate to the environment, start folding down again and bounce even off the surface. And when it does that, it can move. Supposedly. More questions? So that's what I wanted to show you. It's possible that there's some biological relevance for this. So you've seen a lot about motion of cells on 2D substrates and so on. But there's a group at Johns Hopkins here who've in the engineering, so it's this group here of Constantopoulos et al., where they show that you can get cell migration just driven by water flow. Okay? So I'll show you that if we can get this to. Here, yes. Am I connected? Yeah, should work. Oh, okay, I know. Let's play this and then. Does it work? Go back. Okay, we can. Yeah, this should just connect. Okay. It's going. It's got music. I have no idea why they put music. Oh, wait a minute. Why is it? Just a minute. It's not showing there. And through Why is it not showing on the?
You need to go to the settings. This mirror. System preference.
Uh-huh.
System preference.
Oh. Oh yeah, just the mirror displays, right? Yeah.
Display.
We wanted to examine how these confined spaces affected cell behavior. Therefore, we constructed a microfluidic
Gather the
microchannel.
There we go.
When
Yeah.
cells are not confined and migrating on two-dimensional surfaces, they move by
Okay, let's start it
extending
again then.
When cancer metastasizes, cells from the primary tumor find their way to other organs in the body to establish secondary colonies. During their journey in vivo, tumor cells migrate within extracellular matrices and through three-dimensional tracts or microchannels that exist between the connective tissue and the basement membrane of other tissue. This means that cancer cells in the body
What?
within small, micron-sized spaces.
We wanted to examine how these confined spaces affected cell behavior. Therefore, we constructed a microfluidic microchannel.
When cells
Need the microphone here.
and migrating on two-dimensional surfaces, they move by extending leading edge protrusions using actin filaments and retracting the trailing edge using myosin motors. However, for metastatic tumor cells in confinement, we found that cell migration does not require actin or myosin. In other words, disrupting actin or myosin function does not affect the cell migration speed in confining microchannels. This was a real puzzle and raised a fundamental question. How are these cells moving within these channels?
From a physics perspective, this is an exciting question because it suggests that there exists a fundamentally new mechanism. One possibility that came up in our discussions is that perhaps the movement of water in and out of the cell can also drive cell movement. The mechanism works like a small jet. If somehow water is flowing in at the front of the cell and flowing out at the back of the cell can translate forward. Then the question becomes, what can generate this type of water movement? It turns out that the physical process of osmosis can generate water movement across cell boundaries. Imagine that two compartments with different concentrations of proteins and ions are separated by a membrane. Water will flow from the low solute region to the high solute region driven by an entropic force. This will lead to swelling of the high solute region and a movement of the membrane forward. Cells, including cancer cells, have specialized water channels called aquaporins that allow the movement of water in and out of the cell.
In order for this mechanism to work, the cell must establish different solute concentrations at its leading and trailing edges. And as it turns out, cells have a large variety of membrane channels and pumps that can move ions in and out of the cell.
The ionic movements change the local solute concentration, and the cell effectively pumps the water in at the leading end and pumps the water out at the trailing end. We call this mechanism the osmotic engine model.
The mechanism is simple enough that we can write down some mathematics to describe the cell movement. In fact, it's possible to compute the cell migration speed from a simple set of equations. From the theoretical work, it became very clear that external solute concentration in the medium surrounding the cell is an important variable for determining the cell migration speed. In fact, by changing the external concentration, it is possible to reverse the direction of water flow and indeed reverse the direction of cell migration.
This is exactly what we found in experiments. We found that by selectively changing solute concentrations at the leading end and trailing end of the cell, we can reverse the direction of cell migration. This mechanism also predicts a number of other observations. For instance, knocking down water channels in the cell will slow the cell down because it interferes with water flow across the cell membrane. And knocking down ion pumps that are responsible for establishing local ionic concentrations will also suppress the migration speed. The theory also predicts that the important membrane channels and pumps.
Okay, here we can stop. You want to hear the end? Uh-huh. Okay, let's go to the end.
Must not be positioned uniformly on the cell surface. The lead end must have a higher concentration of these membrane channels and pumps, and experiments also verified this.
In this case, it is possible to directly compare theoretical predictions with quantitative experiments and test every aspect of our understanding. Through this type of quantitative experiments and modeling, we can develop better understanding of living systems in other contexts.
From basic science and clinical standpoints, we have a new mechanism of cell migration and therefore a better understanding of metastasis. It is almost as if the cells have two engines, like a hybrid car. The acting myosin engine pushes the cell in nearly all situations, but in confinement, the cell can use another engine that utilizes water permeation. These mechanisms appear to be redundant, but may also explain why cancer cells are so difficult to fight.
Okay, so this is my conclusion. So you can get this shape change driven purely by these osmolarity gradients. The droplet networks can be designed to achieve 3D shapes that are not directly accessible. Otherwise, so you get sort of cooperative folding of these simple cell compartments, and Duan has used these droplet networks to also study transitions between, for example, square and triangular lattices. So if you saw her poster, you would have seen a lot about that, but you can also ask her about that. So, okay, so I'll finish here. Any more questions? Okay, so should we have a short break and Jean-Francois can then just use my last half hour or so. Okay, so let's take a 5-minute break. Thank you.
By cell division. So what I want to do is consider a tissue, and in the tissue, consider a cell that divides. Now, in order to divide, the cell must grow, and it must push on its environment. Now, which means that there are forces exerted by a cell on its environment. And for the same reason that Christina told you 2 days ago, the total force on the dividing cell must vanish. So the total force exerted by one cell on the environment is 0. Then you can make a multiple expansion like you would do in electrostatics. And the first term that you get is a force dipole. So what I'm kind of saying here is that a dividing cell exerts a force dipole on its environment. So the force dipole is exactly like Christina showed you. There are two forces like this. I'll call this one F and this one minus F. And they must be aligned, otherwise there would be a torque, and we don't want any torque to be exerted on the environment. And I'll call D the vector which is here. Now the force dipole is a tensor. It's just a tensor Q alpha beta, which is F alpha d beta. So it's just a product of the force multiplied by the distance between the 2 points. Now, of course, a cell that divides pushes on its environment. I could do the same reasoning with a cell that dies, and the dipole would be in the other direction. Now, what I want to do is introduce a total force dipole density. So I will call that Q alpha beta I point R. It's the sum over all cells. So I consider here all cells that divide and all cells that die. These are all the cells exerting force dipoles. And I put a Latin index for the by numbering these cells. And then I have Q alpha beta I. This is the force dipole of cell I times delta of R minus Ri. So there's a contribution of cell I only if it's at position R, and that will give me the force dipole density. Now what I want to do is write the force balance in the tissue. Taking into account the effect of all the dividing cells. Now, the cells have an elastic modulus, as I told you yesterday. The tissue itself will have an elastic modulus, which is of the same order as the elastic modulus of the cells. So the forces per unit volume will be the elastic forces plus these force dipoles. So the total force is d beta sigma alpha beta elastic, which is the force per unit volume exerted due to the elasticity. And then I have to sum of all these forces here. So plus sum over I, which is again all the dividing or dying cells. And I will have minus F I delta of R minus Ri plus Fi delta of R minus Ri. This is, and that should be 0, because the tissue is in mechanical equilibrium. What I will do then is exactly do what Christina did 2 days ago, which means I will do a Taylor expansion, there should be a parenthesis here, with this variable di. So this will give me d beta sigma alpha beta elastic plus, so this is Fi. So it's, I should put Fi alpha here and Fi alpha, because I write the components, and Fi alpha. So I want to expand here. So sum over I, Fi alpha. Then I will have di minus di beta. And then the derivative of this function here, d beta of delta of R minus Ri. And if you look in here, you have AFI alpha di beta, which is QI alpha beta. You have the delta of R minus Ri, which is here. And this reconstitutes this Q alpha beta, which is here. So I can rewrite this force balance equation, d beta sigma alpha beta elastic plus d beta, there's a minus sign, minus d beta, and sum over I of qi alpha beta delta of R minus Ri is just the force dipole density, so it's Q alpha beta. Sorry, I can't hear you.
Sorry, I missed. What's delta alpha beta?
Where is? Sorry, this is a sigma. I'm just writing the force balance. I include that, and I'm doing a Taylor expansion to first order of this term. Now, of course, what this tells me is that this Q alpha beta acts as an internal stress in the tissue, and this is an internal stress due to cell division and cell death. So I will define the internal stress sigma alpha beta internal, which is minus Q alpha beta. And then in the tissue, everything happens if I had as if I had a total stress. Sigma alpha beta equals sigma alpha beta elastic plus the internal stress internal. And the force balance in the tissue is just that the divergence of this stress is 0. So d beta sigma alpha beta is 0. So that's what force balance in the tissue gives me. What I want to do now is discuss these two terms and see what this equation leads to. In order to do that, I will separate the stress into two components. One is a diagonal component, and one is a traceless component. So I will write the total stress as sigma alpha beta equals some sigma delta alpha beta plus a term that I call sigma tilde alpha beta, and I will impose that sigma alpha alpha, which means the trace of this stress here is equal to 0. So sigma tilde alpha alpha is equal to 0. So what's sigma? Can anybody tell me what sigma is? Sigma is minus the pressure. So minus sigma is the pressure. Okay? So, and I will discuss independently this term and this term. This is the longitudinal component of the stress, and this is a transverse component of the stress. So let me discuss the longitudinal stress. Sorry?
This presumably would be equal to some elastic moduli.
So yes, the elastic one is an elastic modulus. The transverse one is more, the internal stress is more complicated, and that's what I have to discuss.
Right.
So the longitudinal stress. So sigma is sigma elastic plus sigma internal. So what is sigma elastic? It's the longitudinal component of the elastic stress. So it's just the stress due to the compressibility of the system. So sigma elastic is just the compressional modulus times delta V over V. But delta V over V is just a divergence of the deformation. So I note U gamma gamma, where the deformation in each direction is U. And this is just a divergence of the deformation that gives you the change in volume, the relative change in volume in the system. For a reason that you will see in a minute, what I will write is not the stress itself, but the time derivative of the stress. So d dt of sigma elastic is just a compressional modulus chi times the derivative of the deformation tensor. But the derivative of the deformation tensor is just the velocity gradient tensor, or the shear rate tensor. So I will write just chi v gamma gamma, where the shear rate tensor is v alpha beta equals 1/2 So that's kind of trivial. I'm just saying that the tissue is an elastic modulus, and I'm just considering the isotropic mode of deformation of the tissue. Now, of course, the interesting part is the internal stress. The main point is the internal stress is due to cell division and cell death, because it's only the cells which are dividing and dying that contribute to it. So the absolute value of the stress itself is not well defined, because it's only due to the change with time of the number of cells. So what's easy to discuss is the variation with time of this internal stress. So what I want to do is write sorry?
Why is it when you write the rate of the stress,
Oh.
on the right-hand side?
Why isn't chi a function of time? Chi is the elastic modulus of the tissue. It won't change very much with time. If I don't make huge deformation, it will. I assume linear elasticity, and I don't want to go beyond that.
Why is it only proportional to? Why is it not the field?
This is what? I didn't understand your question.
It's only proportional to the strain, not to the strain.
No, it's proportional to the strain. So that's the strain, but when I take the derivative of the strain is the velocity gradient.
Oh, that's the velocity, I'm sorry.
Yeah, where v is the velocity.
Okay, I'm sorry.
So let me discuss the internal stress now. So what I want to discuss is d sigma internal dt. And I will kind of make a phenomenological or empirical estimation of that. It's proportional to the number of cells which divide. All the cells have the same probability to divide. So it will be proportional to the cell density. So there will be rho here. If it's proportional to the number of cells that divides, it should also be proportional to the cell division rate. And then I should make a force that the cell dividing exerts on the surrounding. So I will call that QD. Now, as I said, the stress is minus the pressure. When a cell divides, it exerts a positive pressure. So the stress is negative. So I'll put a minus sign here. So that's the contribution of one dividing cell. This is the density of the average density of cells, and that's the probability per unit time that the cell divides. So it gives me the variation of the internal stress with time. So that's the contribution of cell division. I have an equivalent contribution of cell death plus rho Ka QA.
Could you repeat what QD is?
Okay, I can't hear you.
Could you repeat what QD is?
So I'm saying the stress, the idea of this stress is that it's based on the pressure exerted by each cell on its environment. That has a value when the cell divide, and that's what QD is. Okay? Any other question?
Yeah, basically exactly what KD is the rate of
KD is the rate of division. QD is the pressure exerted by the dividing cell on the environment, by a single dividing cell on its environment in the correct units. It's just trivial. I say this is the force exerted on one cell times the number of cells that divide per unit time. That's what I'm saying here. And same thing for the dying cells. Okay, what I want to do now is look at what happens close to what I call the homeostatic state. So I want to go close to the homeostatic state. Now, what I told you this morning is that at the homeostatic state, the cell division rate is equal to the cell death rate. So QD, KD minus KA, calculated for sigma equals minus pH. Minus sigma is the pressure. So if the pressure is the homeostatic pressure, KD is equal to KA. So this is equal to 0. Now I can do, again, an expansion around the homeostatic state. That will tell me that KD minus Ka. So the zeroth order term is 0. And then I will have a term that goes like sigma plus pH at linear order, and a prefactor that I call kappa. Now I have to check that the sign is right. What I told you this morning is that if I increase the pressure, Kd decreases. But if I increase the pressure, sigma is minus the pressure. So this becomes more negative, and Kd decreases. So this kappa here has to be positive. So that takes care of KD and KA. Now, if I am at the homeostatic state, the tissue is in a steady state. Now, suppose that I divide once, so one cell divides and one cell dies. If one cell divides and one cell dies, I should go back to the homeostatic state, and the mechanical state of the tissue should be the same. Now, the force exerted by one dividing cell is QD. The force exerted by one dying cell is QA. And if I sum the two, I should go back to the initial state. So QD plus QA should be equal to 0. It's just that I want to come back to the original state when I do a cycle on one cell division and one cell death. So I will let QD equals minus QA equals Q. What I will do here to make things simple, but I could include it, is I will assume that this remains true in the vicinity of the homeostatic state. Then I can plug it back into here. D sigma internal dt equals minus rho. There is Q here, and then there is kappa sigma plus pH. Now I sum this and this, so I have the derivative of the total stress. So for the total stress now, d sigma dt equals chi v gamma gamma minus rho q kappa times sigma plus pH. So that gives me what I told you I was looking for this morning. It gives me a constitutive equation. What I mean by that, it gives me a relationship between the stress sigma, or the trace of the stress, which is the pressure, and the velocity gradient. And as I'm looking at the longitudinal term, the only thing that can come in is the trace of the shear rate, which is the divergence of the velocity. So this V gamma gamma is the divergence of the velocity. Now I will rewrite that in a simpler way. I will introduce sigma bar equals sigma plus pH. And this here is the inverse of a time because it should be homogeneous to what's in here. So I define a time tau, which is 1 over rho kappa q. So the total stress is just d sigma bar dt plus sigma bar over tau equals chi v gamma gamma. So as I said, this gives me a constitutive equation. It relates the stress to the velocity gradient. And this equation looks what you all know, which is which viscoelastic model? It's a Maxwell model. Although there is something very special in this Maxwell model, which is what? If you take a complex fluid, the Maxwell model is true for the shear deformation, but it's not true for the bulk deformation. Here, what I only consider is the bulk deformation, is the pressure. So what this tells me is that whatever I do, this will relax to 0. So the pressure will relax to a finite value. Whatever I do, if there is no flow, the pressure relaxes to the homeostatic pressure. The pressure sigma bar will relax to 0, so the pressure will relax to pH. So if there is no flow, which is what I told you this morning with my small drawing, my thought experiment. I told you if I displace the wall, I will reach the same pressure. I wait some time. I wait the time that cells divide, and P relaxes to pH. Now, it's not so common to have and I must admit I don't know of any other example, to have a fluid where the isotropic component follows the Maxwell model. If you take a normal fluid, like a polymer or anything, the pressure is essentially constant or is related to the compressibility of the material. Because of cell division and cell death, in a tissue like this, it always relaxes to the homeostatic stress. There is another difference, which is if you consider incompressible tissue. In an incompressible liquid, the divergence of the velocity is 0. That's the incompressibility condition. If you take a tissue, what I wrote this morning is d rho dt plus divergence of rho v is equal to cell division minus cell death. Now, if rho is constant, this term vanishes times rho. I can take rho out, divide by rho, and this tells me that divergence of V is equal to KD minus KA. So even if the tissue is incompressible, the divergence of the velocity is non-zero. The divergence of the velocity is non-zero because the number of cells is not constant, and the incompressibility condition is just given by that. Sorry? And then there's a third point, which is, you told me that this was a Maxwell model. So here is the compressional modulus. There is a viscosity associated to that people call the bulk viscosity. So what is the viscosity associated to this equation? I have the time, relaxation time here. I have the compressional modulus here. What is the viscosity? Sorry, wait. Chi times tau. So I have a longitudinal viscosity in the tissue, but it has all these properties that I said here, which is the same thing that I said this morning by saying that the tissue was infinitely compressible. It's infinitely compressible because the pressure, if I wait for one division time, is constant and it's equal to pH. So that's for the longitudinal component of the stress. What I want to do now is discuss the transverse component of the stress. So the transverse stress sigma tilde alpha beta. As before, it's the sum of a component which is the elastic component, sigma tilde alpha beta, plus elastic internal. So it's the same story as from the longitudinal component. What's easy to discuss is the elastic stress. So the stress this time doesn't involve the compressional modulus, it involves the shear modulus. So sigma, and I will write directly the derivative, so d sigma tilde alpha beta dt is proportional to the velocity gradient because I took the derivative. So v tilde alpha beta And here is the shear modulus mu. I think in general people put a factor of 2 here, which I will skip, otherwise I will forget it all over. Except that this is traceless. So if I want to write this equation correctly, I should subtract the trace of the velocity gradient. So what I call V tilde alpha beta is 1/2 plus minus 1/3 delta alpha beta minus 2/3 V gamma gamma. So I write it in such a way that if I take the trace of this tensor, the trace is 0. And in order to do that, I have to subtract this value of the trace here. So that's what happens for the elastic part. There is nothing special. The only thing which is special is that I write the time derivative. So what I want to discuss now is the internal stress. So I'll do it the same way as I did before. D sigma So again, it's due to cell division and cell death. And just to make my life simple, I'll only write the term which is due to cell division. So I will put a minus sign as I put a minus sign before. It's proportional to the density of cells. It's proportional to KD. There will be some kind of intensity of the stress exerted by each cell that I write Q tilde D. But then this is a traceless tensor. So I need to put here a traceless tensor. Now, how do I make a traceless tensor in a dividing tissue? There is an axis for cell division, because cell division is oriented. It's the axis at which the spindle is pulling. So I can define an orientation of the cell division, which is the orientation of my vector D above, and I call the unit vector associated to that N. So the unit vector along cell division I call N, and for cell I is Ni. Now, if I have a vector, there is only one way to make a traceless tensor. I define a tensor that I call the orientational tensor, Q alpha beta, which is N alpha N beta. That's a tensor. It's not traceless, so I have to subtract the trace, which is minus 1/3 delta alpha beta. And then if I want to see what happens around a given volume, I will average over all the cells in a small volume. So I put Q alpha beta here. So that's what the physics tells you. Now you have to worry a bit about what this means. Suppose there is no stress in the tissue. If there is no stress in the tissue, it's isotropic. If it's isotropic, Q alpha beta is equal to 0. Now what people know, and that's an experimental fact, is that there is a coupling between the orientation of cell division and the stress in the tissue. Now, the simplest experiment that I know was done by my colleague, who is called Mathieu Piel at Institut Curie. He considers one cell, and he lets it divide, but he puts it on an elastic sheet. So if you put the cell on an elastic sheet without doing anything, the axis of cell division is random. Then he pulls on the elastic sheet, so he's stretching the cell when he does that. And with a very high statistics, I don't know, 90% or something like this, the cell always divide along the axis of the stress. So you pull in this direction, and the mitotic spindle is always in the same direction. What this means is that if the same thing is true in a tissue, there is a relationship between this orientational tensor, which orients cell division, Q alpha beta, and the stress in the tissue. If I want to make a linear theory, I can just write that Q alpha beta equals sigma alpha beta, and then I will divide by a constant, sigma naught. And what sigma naught tells you is what kind of stress do I need to exert to orient the cell division. Now I can write that here. So it tells me that this is equal to minus rho kd qd sigma alpha beta. So I should put a tilde here because, again, I need a traceless tensor. And I have sigma naught. Then I can look at the dimension of this factor, which is here. Again, this is a time. It's different from the other one. So I will write that the derivative of the internal stress with respect to time is minus sigma tilde alpha beta divided by a time tau a. So I do the same thing as with the isotropic part. Yes?
Sorry, I'm a bit confused with the geometry.
Yes?
You say that the cell division happens along the
The axis of the stress, yeah.
So you mean that the plane of division is perpendicular to the axis?
So I'll make a drawing. It's easier than saying words. When a cell divides, it makes a spindle, which is like this, that you saw in Jennifer's talk the other day. What I'm saying is that if the medium is completely isotropic, this axis, which is my n vector, is randomly oriented. Now, what the experiment says is that if you pull like this, which is the principal axis of the stress, it divides in this direction. They did even more crazy things. They managed, so how did they do that? They managed to turn the orientation of the spindle by pulling in the other direction. So they stop, it starts dividing in this direction, and then they pull in the transverse direction, and the spindle rotates. Takes a half hour, but they were patient enough, and they saw it. Now, you agree with me that if I say that Q alpha beta is proportional to sigma alpha beta, they have the same eigenaxis, and it more or less forces that. So then I can calculate the total stress. So D so I have this mu. Where is my mu? The elastic stress was mu P tilde alpha beta minus or if I rewrite it by putting this term here, d sigma tilde alpha beta dt plus sigma tilde alpha beta over tau a. So again, what I find, this is the velocity gradient. This is the stress. At short times, this term is negligible. So the stress is proportional to the strain, and the coefficient is just a shear modulus. At long time, this term is negligible, and the stress is proportional to the shear rate, and the prefactor is the viscosity. So what this means is that if I look at times longer than tau a, the tissue is a viscoelastic liquid, and it flows with a shear viscosity which is eta equals mu tau a. And there's nothing special. If you take any complex fluid, most of them follow a Maxwell equation like this. And if you look at the traceless component of the stress, it does indeed follow this Maxwell equation. So that's a standard viscoelastic fluid. Now, I cheated you somewhere. Well, before you tell me that, I need to give you an order of magnitude of these times. It's always related to cell division, So the right order of magnitude of these types must be the cell division time. So both tau and tau A, I don't exactly know where they are, but they should be of the order of the cell division time, which means 1 day. So where did I cheat you? I mean, I didn't cheat you, but I did something without telling it on purpose that led to this result, which is what? I did what? I only considered the division. Yeah, so then if there was a term related to apoptosis, instead of having KDQD, I would have KDQD plus KAQA.
But do you still have the same dependence on?
No, because now the tissue is not, I need to shear it. And so the fact that it's at a homeostatic state doesn't tell me anything about QD and QA. So yes, it's true, but it doesn't change the result. It changed numbers in the end, but that's what it does. I did something worse than that, which is okay, but I introduced this tau A here, which had some expression that was this term here. I just imposed on you that this was a positive number. But nothing tells me that it's a positive number, as there could be tissues from which tau A is negative. What should I do in this case? So tau A negative. Or if you want, sigma 0 smaller than 0. So that would tell me, I will write sigma 0 equals minus sigma 1. So it will tell me that sigma alpha beta tilde is equal to minus sigma 1 q alpha beta. And that wouldn't be okay because it would mean that the stress diverge. So I have to do some things to avoid the divergence of the stress. So how should I do that? I can view that. I didn't hear what you say. Yes, that might change. So what I could do is say, this is kind of an order parameter. This is kind of a field. If this is positive, the susceptibility is positive and everything is stable. If the susceptibility is negative, it means that the state with 0Q is unstable. And then you know what you have to do. You do a Landau expansion. So plus, and then there would be a term Q alpha beta, no, Q alpha gamma, Q gamma beta. Which is exactly what you do when you do a mean field theory of the isotropic nematic transition, except that you call that a field, I call it a stress, but it doesn't matter very much. And what's the output of that? The output of that is that there is a finite value of Q alpha beta at equilibrium. What this means is that your tissue is oriented. So there is a spontaneous polarization of the tissue.
Is this something more experiment?
Sorry?
Experiment is there?
Yes, that exists experimentally. There are tissues which are spontaneously polarized. And this would be a mechanism that spontaneously polarizes the tissue. And then if I do that, instead of expanding around 0, I expand around the average value, and everything comes back to normal, and I am again back.
Can you remind me, what's the control parameter?
That would be sigma 1. But the sigma 1, I don't know what it is exactly. For a given tissue, it's fixed. It tells me how much cell division depends on stress. And that depends on the properties of individual cells. Now, one issue, at least one thing that was said to me by somebody called Yves Couder, that some of you might know, is that, of course, this exists. This is what happens for plants. And plant tissues are always polarized, more or less. There is a major difference because the cells in plants have a cell wall. So the coupling between stress and cell division is completely different. And when I told that to Couder, he told me, yeah, that's true, that's how plant works. I'm not so sure, I don't know much about plants, so, but at least there is a suggestion here. But if there is a spontaneous polarization of the tissue, so my tissue is nematic, the cells are elongated if you want, there is something else that happens. That brings me to the first lecture that I gave. The cell consumes energy, it's oriented, I showed you that it's fluid. These are all the criteria that I had for an active system. So in this case, not only should I continue the expansion, but I can add to the stress an active stress. So in this case, there should be an active stress. So if there is a spontaneous polarization, the fact that the tissue is active, in a sense that it consumes energy, becomes relevant for the mechanics. And then I can use the whole machinery that I told you yesterday, or that Christina told you 2 days ago. It's exactly the same equations. But now I can use it for the tissue. It's a viscoelastic active fluid. Is that clear? I'm kind of done with what I wanted to tell you. Is that clear for everyone? Okay. So thank you very much. So you curved your paper?
Huh?
You curved your paper?
I guess I don't sweat enough.
You can float it on water. And Sorry?
You wrote this up.
Oh yeah, a few years ago.
Okay, I'll try to intercept what it is.
It's PNAS, and the first